Welcome to the deep dive. Today we're jumping into carbonyl compounds. That's aldehydes and ketones.
That's right. Really fundamental stuff in organic chemistry. And the main player is that carbonyl group, the CEO double bond.
And what's special about that bond?
Well, it's all about the oxygen. It's more electronegative, so it pulls electron density towards itself.
Ah, like an electron hog.
Exactly. Leaves the oxygen slightly negative, and importantly, the carbon slightly positive. Electrophilic.
So that positive carbon is like a target.
Precisely. It's attracting electron-rich species, the nucleophiles. That polarity is really the key to almost everything they do.
Okay, and we have the two main families, aldehydes, with an H on the carbonyl carbon.
At least one H, yeah, RCHO.
And ketones, with two carbon groups attached, RCOR.
Right. Alkyl or aryl groups usually.
So our mission here is to explore how these react, especially through nucleophilic addition and condensation, and kind of see where they show up.
Sounds good. Nucleophilic addition is probably the place to start.
Right. How does that work generally?
Okay, so imagine your nucleophile, electron-rich. It sees that slightly positive carbon.
The target.
A target, yeah. So step one, attack. The nucleophile hits the carbon. At the same time, that pi bond in the CO breaks, and the electrons jump onto the oxygen.
Forming an intermediate.
Yep, an alkoxide intermediate, oxygen with a negative charge. Then, step two usually is protonation. It grabs a proton, like an H plus A, often from water or a mild acid added later.
And you end up with an alcohol derivative.
Exactly. And interestingly, the carbon atom's geometry changes. It goes from flat, spe-hybridized.
Terminal planar about 120 degrees.
Right. To tetrahedral, spe about 109.5 degrees. So the shape changes quite dramatically during the reaction.
Now, I remember reading that aldehydes tend to react faster than ketones in these additions. Why is that?
Two main reasons, really. First, sterics or just crowding. Aldehydes only have one R group and a small hydrogen atom.
Less stuff in the way.
Right. Ketones have two R groups, which can be bulky, making it physically harder for the nucleophile to get in there. Second is electronics. Those R groups, alkyl groups especially, are weakly electron donating. They push a little electron density towards the carbonyl carbon.
Okay.
So with two R groups, a ketone's carbonyl carbon is slightly less positive than an aldehyde's, which only has one R group helping out.
Making it a less attractive target for the nucleophile.
Exactly. Less positive charge, less attraction.
Makes sense. Can you give us a few quick examples?
Sure. Reacting with HCN, hydrogen cyanide makes cyanohydrins, very useful. Or Grignard reagents, RMGX.
Oh, yeah. Carbon nucleophiles, great for making bigger molecules.
Totally. They add in, and after an acid workup, you get alcohols. Primary alcohols from formaldehyde, secondary from other aldehydes, tertiary from ketones.
Versatile. What else?
Alcohols can add under acid catalysis to form hemiacetyls and then acetyls.
Yeah.
And primary amines, RNA heroes, react to form an imines, sometimes called Schiff bases, after losing water. Important biologically.
Okay, lots of options. Now, something called the electromeric effect came up. What role does that play?
Ah, right. That's a temporary effect. As the nucleophile gets close, its negative charge sort of encourages the pi electrons in the CO bond to shift fully onto the oxygen.
Even more than the usual polarity.
Yeah, it's like a temporary, complete shift induced by the attacking reagent. It makes the carbon even more positive just for that moment, facilitating the attack. It's called a negative electromeric effect, or E-UVA effect here.
Interesting. Okay, let's shift gears to building bigger things. Carbon bond forming reactions, like the aldol condensation.
Yes, the aldol, super important. This involves a carbonyl, an aldehyde or ketone, that has hydrogens on the carbon next to the carbonyl group. We call those alpha hydrogens.
Okay, alpha hydrogens are key.
They are, because a base can remove one, forming an enolate ion, and that enolate is a great carbon nucleophile.
Ah, so it makes its own nucleophile.
Kind of, yeah. And that enolate then attacks another molecule of the original carbonyl compound.
Connecting them together.
Right. You initially form a beta-hydroxy carbonyl, the aldol product. Often, especially with heat or base acid, this then loses water.
Dehydration.
To form an alpha, beta-unsaturated carbonyl, an anone or enol. It's fantastic for building carbon chains.
Can you give a simple example?
Sure. Take acetaldehyde. Treat it with a dilute base. One molecule forms an enolate, attacks another acetaldehyde. You get the aldol product, which then dehydrates to crotonaldehyde.
Okay. What if you mix two different carbonyls?
That's a crossed aldol. It can get messy, potentially giving you 4 different products if both have alpha hydrogens.
Bit of a lottery then.
Can be, but it works well if one partner doesn't have alpha hydrogens, like benzaldehyde, It can only act as the electrophile.
Ah, okay. Like the Claisen-Schmidt reaction.
Exactly. Benzaldehyde reacting with, say, acetone gives you dibenzolide and acetone. Much cleaner.
Then there's the Cannizzaro reaction. Sounds different.
It is quite different. It's for aldehydes that have no alpha hydrogens, benzaldehyde again, or formaldehyde.
So they can't form an enolate.
Right. What happens instead in strong base like concentrated KOH is disproportionation. One molecule of the aldehyde gets oxidized to the carboxylic acid salt.
Loses electrons.
And another molecule gets reduced to the corresponding primary alcohol.
Gains electrons. Okay.
Yeah.
Like a redox reaction with itself.
Basically, yeah. Base attacks, hydride ion transfers. Benzaldehyde, for example, gives benzyl alcohol and potassium benzoate. There's also a crossed version, often using formaldehyde, which readily gets oxidized.
Got it. Quick mentions. Benzoin and Perkin condensations.
Sure. Benzoin is coupling two aromatic aldehydes, usually with cyanide catalyst, to make an alpha-hydroxyketone, like benzoin itself from benzaldehyde. Perkin makes alpha-beta unsaturated aromatic acids from an aromatic aldehyde and an acid anhydride using a weak base. Benzaldehyde plus acetic anhydride gives cinnamic acid.
Okay, lots of named reactions there. Now, practically speaking, how do you tell aldehydes and ketones apart in the lab?
There are some classic qualitative tests. Toland's reagent gives a silver mirror with aldehydes. Feeling solution gives a red precipitate. Schiff's reagent turns magenta. Ketones generally don't react.
Simple enough. Any catches?
Well, alpha-hydroxyketones can sometimes give positive tests with Toland's or feelings, so you have to be a bit careful.
Good point. Finally, these aren't just textbook examples, right? They're used everywhere.
Absolutely. Formaldehyde for resins, disinfectants. Acetone is a huge solvent. Benzaldehyde is almond flavoring. Vanillin is, well, vanilla. Cinnamaldehyde gives cinnamon its flavor and smell. Uses in polymers, perfumes, pharmaceuticals, agriculture. It's a long list.
So it really comes back to that polar CDO group driving all this diverse chemistry.
It really does. Understanding these fundamental reactions is key to synthetic organic chemistry, letting us build complex molecules for all sorts of applications.
It's fascinating how subtle structural differences, like just having an H versus an R group, lead to such different reaction pathways and uses. Makes you wonder, what other small molecular features are out there just waiting to unlock completely new types of reactivity and applications?
That's the beauty of chemistry, always more to explore.
Indeed. Well, thanks for joining us on this deep dive into the world of aldehydes and ketones.